Good evening. Today we will be solving some questions based on Scott connection and parallel operation of transformers. So we have a question. A Scott connected transformer takes power from a 33 kV line, three-phase supply, and delivers power to two single-phase 50-volt furnaces with power factor 0.75 lagging. Furnace 1 consumes 150 kilowatt and furnace 2 consumes 100 kilowatt, and both these furnaces are operating at same voltage, that is 50 volt. Okay, now you know that Scott connection is achieved, that it is a three phase to two phase conversion using two identical single phase transformers. We have a teaser transformer and a main transformer. We tap the main teaser transformer to root 3 by 2 times of the original number of turns, and for the main transformer total number of turns are applied. How this is achieved? This is achieved using the triangle property. We knew that in the triangle the median in a triangle, if these are, this is VAB, this is VBC and VCA, then and the median, the ratio, let this be point n, then this ratio is 2:1. This ratio is 2:1. And what is the length of this line? That is root 3 by 2 times of V, any of this line voltages, and this is 2:1. Utilizing the above concept, we will see these two single phase transformers are there, N1 and N2 turns, with primary as N1 number of turns and secondary as N2 number of turns. These two transformers are connected such that we are able to get balanced two phase from balanced three phase input. So they have asked in the question that estimate RMS value of current IA. Okay, that means they need this current IA. What we need to do, we have already known the load connected to furnace 1. Load connected to furnace 1 is 150 kilowatt. 150 kilowatt. Okay. Power factor is 0.75 lagging. So you can get the kVA by dividing the power factor. So furnace 1 is consuming 200 kVA. Now what we need to, if we assume that input kVA equal to output kVA, assuming no losses in the system, then we know that input voltage is 33 kV, output voltage is 50. Okay, so by equating both side kVA, we can get the current. So IF1 will be SF1 divided by 500. So we get 4 kiloamps being drawn by the furnace 1. So we can now apply the turns ratio. We know that the voltages are in direct proportion to the turns ratio, and the current drawn is in inverse proportion. So from there we apply this proportionality, and from where we get that current drawn is 6.998, almost 7 amperes. Now they are asking estimate the current IB, that means line current in phase B. Okay. So we know that first we need to find out the kV of second furnace. kV of second furnace can be obtained by dividing by the power factor. Now similarly, once you are known the kVA, divided by the voltage to get the amount of current. Same logic as we have done in the previous section. So we get current as 2666.66 amps. Now again similar turns ratio are inversely proportional to the current drawn. So the current entering in terminal B and leaving out through terminal C, let me call it as IBC, that is the total current. Okay, so IBC will be by that from the turns ratio formula it comes out to be 4.04. Now if you look at this diagram, we have current IA coming from A, and at this middle point this winding is split into exact half number of turns, N1 by 2, N1 by 2. So the current IA will split into two parts, that is IA by 2 and IA by 2. So the current IB can be said as IBC minus IA by 2, vector sum of IBC minus IA by 2, and similarly IC can be said as IBC plus IA by 2. Remember that these both current are 90-degree shifted to each other. So to obtain their magnitude we need to have the vector sum. So IB is IBC minus IA by 2, so that lands up to 5.345. Similarly IC will be, so we can see that a two-phase three-phase to two-phase conversion is happening using this Scott connection. Now next question we have a parallel operation of transformer. We have been given two single phase transformers which are operating in parallel. Transformer 1 ratings are 300 kVA, 6600 by 240 volt. Per unit impedance is given as ZE is 1 plus J 4.25%. Similarly, transformer 2 is 200 kVA, 6600 by 230 volt, and per unit impedance is 1.25 plus J 5.5%. Now the high voltage sides are parallelly fed from 6600 volt bus. That means the transfer input to both of these transformer is 6600 volt. Now before we start the calculation we need to get actual values of their impedances. So base value of impedance can be found out, Z base can be found out by V square by the kVA base. So for the respective transformers we will use their ratings and find out the Z base. Z base comes out to be 0.192 ohms. Similarly find out the Z base for transformer 2. Bases will be different because their ratings are different. So we are getting this Z base for transformer T2 as 0.2645 ohms. Now we need to get actual. So how will you get the actual? Actual value will be obtained by multiplying the per unit value by the base value. So multiply this, you are getting this 1.92 plus J 8.16 into 10 power minus 3 milliohms. Similarly for J base, the actual base Z actual or transformer T2 we'll multiply by the per unit into by the base value, we are getting this. Similarly, we are getting this 3.3 plus j 14.45 into 10 power minus 3 ohms. Now we are knowing the actual values of the transformer impedances. Now under no load condition, when these transformers will be connected, there, since they are not having exact x by r ratio, and also the no load voltage is also different, we will have a circulating current flowing. So circulating current can be found out by this is 240 angle 0, this is 230 angle 0. Their output voltages are 230 and 240. Since they are operating in parallel, we can assume that current is moving from point A, something let me call this as x, sorry, x, y, then current will move from point x to y and then back to x in this way. This will be the circulating current represented by IC. So IC will be 240 angle 0 minus 230 angle 0 by summation of both the impedances. So that we get at IC as 492.36 angle. So magnitude is 429.36 amperes. Now they are saying estimate the ohmic losses due to this no load circulating current. Ohmic losses will be contributed due to I square R loss. So IC is known to you. So IC square into summation of actual resistance from the total impedance, we will multiply and we will get I square R. That is something, then ohmic loss is 926.3 watt. Okay. Now they have asked estimate the no load side voltage. So no load side estimate the no load low voltage side terminal voltage. So what we know the circulating current, and they have asked the no load voltage VAB. The no load voltage will be 240 angle 0 minus I circulating into Z actual T1. That find out using the complex calculation, you will get 236.4 volt. So in parallel operation of transformers, we have two conditions. Let us say that the transformers have same turns ratio, same voltage ratings, same x by r ratio. Under that case, when transformers are paralleled, we can simply say that the transformer with least value of per unit impedance will reach its full loading first, or will share the maximum load inversely related to their impedance on per unit. These conditions can be directly applied only when transformer has same voltage, same x by r ratio. Remember, and in case when transformer voltages are different, turns ratios are different, so in that case we need to, for parallel operation, we need to proceed using Millman theorem. This we need to proceed using Millman theorem. In Millman theorem, we need to first calculate the input impedance seen in the terminals across which the transformers are parallel. Then by short circuiting the terminal, we need to calculate the short circuit current. So the voltage which will be appearing across the load when transformers are operated in parallel fashion, that will be given by multiplication of the impedance seen between the terminals and the short circuit current. This is the Millman theorem. Okay, so ISC will be uh, under EA by ZA, EB by ZB, and similarly your input impedance between seen in the terminals, the impedance, net impedance seen in the between the load terminals can be 1 by Zp is equals to 1 by Za plus 1 by Zb plus 1 by Zl. So here you cannot directly apply this formula that Ia is equals to Zb upon Za plus Zb into Ia is equals to Zb upon Za plus Zb into IL. This is wrong, because this is not the case of parallel. This is not the case for uh, same turns ratio and uh, same X by R ratio condition. Now we have a question. Consider two single phase transformers in parallel. Transformer 1 is 150 kVA, per unit resistance is given as 0.15, leakage reactance is 0.06, and the no load secondary voltage is 415 volt. Similarly, again for transformer T2, 300 kVA, per unit resistance is 0.01, leakage reactance is 0.045, and we have the secondary voltage as 405. We can see that this is the case of different X by R ratio. Okay, so again we will proceed to find out the base values. Base values of T1 is, first we need to get actual values of impedance. So base value will find out by 415 square divided by the base kVA. Similarly, base impedance 2 is 0.045. So actual values can be found out by multiplying these in the multiplying the per unit values by the base values, that are 0.0709 at an angle 75.96 and 0.025 at an angle 77.46. You can clearly see that these X by R ratios are different. Now again, circulating current, we have a difference of 10 volt in both the voltages. So I circulating current can be found out by 10 divided by the summation of both the summation of total uh, leakage impedances, or total impedance of the transformer, equivalent impedance of the transformer. So we get the circulating current as 104.38 angle minus. Now they will estimate the current supplied by transformer when both transformers share the load together. Now transformer, they are sharing the load together. Now we need to go with the Millman theorem. The load to be shared is 450 kVA, 400 volt. Okay, at 0.8 lagging. Okay, so what will be the load impedance? ZL can be found out by VL square by SL. So we will get the load impedance as 0.355 at an angle 36.86. Now find out the net impedance across terminal, this point, load terminal A, and this is B. This is A and this is B. So looking into terminal A and B, we need to find the net impedance. So net impedance, let me call it ZP. So that 1 by Zp will be equal to 1 by Za plus 1 by Zb plus 1 by Zl. So Zp is, after calculation, Zp is 0.0177 at an angle 75.45. Okay. Now Now next step is to find short circuit current. So what will be ISC? ISC will be EA by ZA plus EB by ZB. So short circuit current is 22,052 at an angle minus 77.06. Now what will be the load voltage? ISC into ZP, as I told you in the Millman theorem process, how to find out ISC into ZP. So you get the load voltage as 390.32 at an angle minus 1.84. We have the load voltage as given. So you know that transformer secondary voltage for transformer A is 415 angle 0. Load voltage is 390 minus, you know, ZA divided 415 angle 0 minus 390.32 angle minus 1.84 divided by ZA. So you get IA as 382.36 at an angle minus 52.13. Similarly, for IB, current drawn by from transformer B will be EB minus VL by ZB. Okay, that's all for the parallel operation of transformers. Okay, thank you.